All right, let's just dive right into this explainer. Today, we're demystifying the complex, almost totally invisible system-level engineering that makes massive AI workloads run at those blazing speeds we've all come to expect. You know, we spend so much time talking about model architectures and parameter counts, but we rarely look at the physical and software plumbing that actually makes these models train and run in the first place. So here's the thing. We all know AI runs on GPUs, right? But GPUs are entirely dependent on their supply chain. If the supply chain of the CPU, the memory, and the operating system is lagging, these incredibly expensive machines just sit around starving for data. You're effectively paying top dollar for a world-class race car, and then forcing it to wait at red lights in standard city traffic. It just doesn't make sense. So here's our roadmap to fix that bottleneck. We'll start with the AI hardware bottleneck. Then we're unpacking the software stack, tuning the CPU pipeline, maximizing GPU efficiency, and finally, managing memory and errors. Let's get right into it. Part 2, unpacking the software stack. To fix this broken supply chain, we first need to look at the hidden blueprint that actually controls the flow of our work. Believe me, it's way deeper than just hitting run on a Python script. Look at the sheer height of the NVIDIA software stack here. I mean, there are so many layers sitting between your deep learning framework and the actual silicon. It's so much more than just writing a line of code. Sure, you've got your high-level PyTorch, but right underneath that there are domain-specific libraries, accelerated libraries like cuBLAS, compiler stacks like NVCC, and host runtimes. Every single layer in this giant puzzle can impact your final performance. If literally any one of these is out of date or misconfigured, the whole entire stack suffers. To put that into perspective, let's see how this actually plays out in the real world. When you execute a seemingly simple tensor operation in PyTorch, that single Python call translates through this crazy complex sequence. It moves through C++ bindings, hits a backend dispatcher, utilizes the CUDA runtime API, and only then, finally, does it actually execute as a kernel on the GPU device itself. Honestly, understanding this specific journey is what turns you from a standard AI developer into a true systems-level performance engineer. Moving on to part 3, tuning the CPU pipeline. Now that we understand the stack, we've got to optimize the factory conveyor belt itself, which is the CPU and the operating system. Their entire job here is just to keep our GPU fed. Okay, so there is a massive silent killer of AI performance, and it's called a lack of NUMA affinity. NUMA stands for non-uniform memory access. Simply put, this means binding a process and its memory to the specific CPU core that physically resides on the exact same node as your target GPU. If we don't use NUMA affinity, our memory access latency can nearly double. We're talking jumping from roughly 80 nanoseconds to almost 140 nanoseconds, literally just by crossing over to a different physical node. It stops our assembly robot dead in its tracks. You can actually see the physical distance here, spanning between NUMA node 0 on the left and NUMA node 1 on the right. If GPU 4, which sits over on node 1, needs data, the process feeding it better be running on a CPU core also inside node 1. Because if the OS randomly schedules that data loading thread all the way over on node 0, you incur massive cross-node delays every single time a byte of data is transferred. All right, next up, let's talk about memory. By default, the OS uses what's called pageable memory, which just means it can swap things out to your hard drive if your RAM gets full. Now, for AI workloads, this causes disastrous, multi-order of magnitude slowdowns. We absolutely do not want that. Instead, we want pinned memory. This is page-locked memory. It essentially tells the OS, hey, do not move this. Keep it locked in RAM for high-speed, direct access. And you can see why right here. Copying data from pinned host memory to the GPU completely bypasses all those extra staging steps. The GPU can use direct memory access, or DMA, to reach right into the host RAM and grab exactly what it needs. This one simple change, like literally just flipping pin_memory equals true in your PyTorch data loader, makes data transfers 2 to 3 times faster. No joke. Now, we can squeeze out even more throughput by managing how the OS actually chunks that memory. By default, Linux uses these tiny 4 kilobyte memory pages, but AI datasets use hundreds of gigabytes. Managing millions of tiny pages just exhausts the system. So by enabling transparent huge pages, or THP, we can use 2 megabyte or even 1 gigabyte pages. This relieves pressure on the CPU's address lookups and massively speeds up training. But there is a catch. For latency-sensitive inference workloads, you actually want to disable THP. Why? Well, the background process that defragments these huge pages can cause unpredictable, jittery pauses, which is totally unacceptable when a user is sitting there waiting for an LLM response. Oh, and we absolutely have to talk about power savings. Actually, scratch that. We need to talk about disabling power savings. Servers are designed to save energy by putting idle CPU cores into deep sleep modes, which are called C states. But in an AI context, if a data loader thread is waiting for just a split second and the CPU decides to go to sleep, waking it back up takes precious microseconds. Those micro delays create little bubbles of idle time that entirely starve the GPU. To fix this, performance engineers will lock the CPU frequency to maximum and just disable those deep C states entirely. Moving into part 4. Maximizing GPU efficiency. So, the conveyor belt is optimized, the CPU is wide awake, the memory is locked down, and our data is local. Now, let's focus on maximizing how the GPU actually digests its meals. Did you know that by default, if a GPU isn't actively crunching numbers, the driver literally goes to sleep? Then, when the next job hits, the driver has to spin up and initialize everything all over again, which can take 1 or 2 whole seconds. By turning on GPU persistence mode, we keep that driver loaded and the hardware context ready 24/7. Sure, it slightly increases your idle power draw, but we completely eliminate those annoying cold start delays, so the next job can begin processing instantly. Check out the difference in scheduling here. It's night and day. On the left, without multiprocess service, or MPS, we've got this idle ping-ponging effect. The GPU runs process A, stops, runs process B, stops. It leaves all this blank white space, which is just wasted hardware time. But on the right, with MPS enabled, we eliminate those idle gaps entirely by overlapping work from different processes concurrently. So if you've got a massive 40-gigabyte GPU, but your inference jobs only need 10 gigs each, MPS seamlessly interleaves them, so the hardware is just constantly saturated. So MPS is fantastic for sharing resources cooperatively, right? But here's the catch. It doesn't partition memory. One greedy process could crash everyone else's jobs. So what if we need strict, secure isolation between different users or different jobs on the exact same physical chip? Well, the answer is multi-instance GPU, or MIG for short. Unlike MPS, which is essentially just a clever software scheduling trick, MIG physically slices the actual hardware. It divides up the compute, streaming multiprocessors, the L2 cache, and the memory into up to 7 totally isolated logical GPUs. That means if one user's slice crashes or totally runs out of memory, the other 6 slices just keep humming along perfectly, completely unaware that anything even happened. Looking at these Blackwell B200 profiles, you can clearly see the math of how administrators can cleanly chop up compute capacity and memory. You can take this absolute beast of a machine and literally carve it into 7 smaller GPUs, or maybe 2 medium ones and 1 large one. It's brilliant because it allows you to pack multiple smaller workloads perfectly onto the hardware without wasting a single flop of compute power. And finally, part 5, managing memory and errors. Because when you're pushing this much data at these insane speeds, physics itself starts to get in the way. I am literally talking about cosmic rays. Seriously, a single stray cosmic ray from space can flip a 1 to a 0 in your GPU's memory. This is exactly why error-correcting code, or ECC memory, is absolutely essential. It corrects single-bit errors on the fly. Now, yeah, you can technically disable ECC to get a tiny few percent speed up and a very small sliver of extra memory, but leaving it on is absolutely critical. Just imagine running a $1 million multi-week AI training run only to have the entire model silently corrupted by a single flipped bit, all because you wanted 2% more memory. It is simply not worth the risk. Keep ECC enabled. Now, we also need to get realistic about out-of-memory errors. Modern GPUs and frameworks have these incredible safety nets like unified memory. The page migration engine can easily allocate memory or automatically page out excess data to your slower CPU RAM to avoid an ugly crash. But listen to me here. This is a safety net, not a strategy. Relying on this kind of memory oversubscription means your ultra-fast GPU has to just sit there and wait for data to travel back and forth over the system bus, which drags your performance all the way down to the speed of standard CPU memory I/O. If you find yourself constantly paging to the CPU, you really just need to reduce your batch size or shrink your model. Which really leaves us with this final thought. We spend countless hours tweaking hyperparameters, modifying neural network architectures, and optimizing our code. But as we've seen today,
The invisible hardware and OS settings, things like NUMA affinity, pinned memory, C states, and MPS, dictate whether that code crawls or flies. So ask yourself, are you leaving tens of thousands of dollars in compute time on the table simply by ignoring this invisible software supply chain? Take a hard look at your infrastructure today, and I bet you'll find a bottleneck just waiting to be uncorked. Thanks for learning with me today, and keep optimizing.